Let's continue taking a look at some more integrals with our exponential, logarithmic, and hyperbolic functions. So here we have an exponential raised to the hyperbolic sign, or we could say sinh of 2x times cosh of 2x dx. So we're looking at that and thinking, one, that's not one of my basic integrals, but I can let u equal sinh of 2x and then find my du for substitution. Now my du dx, my derivative, because the derivative of sinh is cosh, so my derivative is going to be cosh, or hyperbolic cosine, of 2x times 2 through the chain rule. And this is du dx, of course, but I think at this point we've done enough substitution. We'll write the dx over here. And since I have a cosh of 2x right there, I'm going to go ahead and divide by 2. So 1/2 du is equal to cosh of 2x, hyperbolic cosine of 2x dx. Then I can make the substitutions. This becomes the integral of u times 1/2, this whole thing right here, 1/2 du. So that's just 1/2 integral of e to the u du. And that becomes just 1/2 e to the u. Plus our integration constant, and we plug our u, hyperbolic sign of 2x, back in, or we could say sinh. So remember, we call hyperbolic sign, we can use the shorthand sinh, and hyperbolic cosine the shorthand cosh. All right, let's keep rolling. Okay, so here's another example. E to the x plus e to the negative x, e to the x minus e to the negative x in the denominator. Now this one, there is some algebra we could play around with. We could pull out like an e to the negative x, and we could manipulate in that way. We could write e to the negative x as 1 over e to the x, and then find a common denominator. And there's a few different things that we could do, but I do notice right away, here is one thing that I look at right away. I notice in the denominator that if I let that be my u, if u equals e to the x minus e to the negative x, well, my du, through substitution, my derivative here, because of the e to the negative x, that becomes negative e to the negative x times -1. So my du is actually a positive e to the negative x dx. And notice that that's what's in the numerator here. And so this actually becomes just 1 over u du. Now so that is one way to do it. As mentioned in the previous video, and as we've been working with integration, there are often more than one way to simplify and integrate, or different substitutions that could be done, or different integration strategies. As we continue to build our integration strategies, there are often more than a single way to do a problem. And so I'm showing you this way, but if you see a different way and you would rather simplify algebraically, maybe before you do the substitution, feel free to explore that on this problem. But we did this, we got the substitution, so this ends up simply being the natural log of the absolute value of u plus c, which is the natural log of the absolute value of e to the x minus e to the negative x plus c. All right, let's take a look at another one. Let's take a look at e to the x over 49 minus e to the 2x dx for specific values of e less than the natural log of 7. Now, I do believe this is actually example number 7. I think I misordered these. So let's go ahead and let me fix that so our numbering will be consistent with the number that we're on. So this is number 7. Now, I'm looking at this and I'm thinking, man, I don't know, like if my denominator, right, like there's some experimentation that we would do, or some thought process, right? If I let u be my whole denominator, 49 minus e to the 2x, then my du is minus e to the 2x times 2 dx. And I only have an e to the x in the top. So, we do want to go through that process, right? We want to practice and see, like, is there a substitution I could do here? Is it a substitution on the whole denominator? And that doesn't quite work. And so then we're thinking, well, geez, in the bottom, it's funny, that little 2 stayed squared, because this is e to the x squared. And this is like a perfect square as well. So this is like 7 squared. In fact, I could pull that all the way out. This is almost like a squared minus a u squared is kind of what we're looking at right here in the denominator. And as I'm looking through that, I'm thinking, you know what? I think there's some substitution I could do, some manipulation, and I could make it look like one of my inverse integrals, one of my integrals of an inverse function. But which inverse function? Is it an inverse trig function? Because it's not inverse tangent, because it's not 49. There's not a plus something squared here, like a 1 plus, but there's a 1 minus x squared. And so I just put this up here. Again, remember, this is in our little set of formulas for the hyperbolics that we've been playing around with and working with. And it turns out that the integral of 1 over 1 minus x squared is equal to the inverse hyperbolic tangent. So remember, the actual inverse tangent has a plus right here. But if we have that 1 minus x squared, it's actually the inverse hyperbolic tangent as long as the absolute value of x is less than 1. So we do have a domain restriction stated here, which will allow us to use that formula. So how do we manipulate it? How do we make it get into that form? Well, what we do here, I'm kind of looking at it, I see the 49 instead of the 1, so I can manipulate the 1 over 49, factor that out of the denominator. So thinking of this, I will write one more step here in between. So we could write 49 times 1 minus e to the 2x divided by 49. And then in this next line, I'm going to go ahead and switch back over to black. This would be, I'm going to pull the 1 over 49 out, and I'm going to write this as 1 minus e to the x over 7 quantity squared. So even taking that e to the 2x over 49 and writing that as a perfect square, e to the x over 7 squared. Now I still have the e to the x in the top, but I'm actually going to just put it out here, e to the x dx, so that I can really see that 1 over something squared. And that something that's being squared, that's going to be my u. So if u equals e to the x over 7, and then du equals e to the x over 7 dx, or 1/7 e to the x, and so e to the x dx, so I can make the substitution, is 7 times du. And now look at this. I can make those substitutions. I still have that constant 1 over 49 out in front. I end up with 1 over 1 minus u squared. The e to the x gets replaced with a 7 du. The 7 can be factored out to the front, and so we end up with 7 over 49, which is going to reduce to 1/7. Integral of 1 over 1 minus u squared du. And so that becomes just 1 over 7 inverse hyperbolic tangent of u plus c. So remember our formula there. And then we can just plop our u back in. So our u was e to the x over 7. So this ends up being 1/7 inverse hyperbolic tangent of e to the x over 7 plus c. And that's our answer. And we did it with a substitution and using the general formula for the integral of 1 over 1 minus x squared being equivalent or equal to the inverse hyperbolic tangent of x. So I wanted to remind you, I'm going to change screens real quick and go back to our reference page because we actually had an extension off that formula that we could have used here as well. Just zooming in here on the bottom part of our reference table from the very first video for this section, we had the integral of 1 over a squared minus x squared, and we can prove that and show that using a quick little u substitution. We can show that that is 1 over a inverse hyperbolic tangent of x over a plus c. Now our x, we did have to do a little substitution on. Our x was actually an e to the x, and so there was a substitution there on that particular problem, but we could have utilized that formula. We were working instead with this formula. That's the formula that we were working with on this problem, the way I showed it, and we did the algebra to get it into that form with a 1 minus u squared, but we could also have left it like this, a squared minus x squared, and used this formula. So again, the more familiar you are with these formulas, you could shortcut your work just a little bit, little less algebra possibly, if you knew both of those two formulas. But again, kind of how you see the problem and how you work through it. Okay, let's wrap this video up with this particular example, but this is kind of a fun one, a definite integral. We're taking the integral from 1 to e squared of dx over x times the square root of the natural log of x squared plus 1. Kind of a lot going on here. And the first thing I kind of notice in this one is, again, like if we think about letting this whole quantity under the root be my u, I'm going to get hung up pretty quickly. I'm going to get hung up pretty quickly in not being able to have something that is du to work with. So then what do? Well, I'm thinking about this and I'm looking at that natural log of x squared and thinking of actually writing it like this. And when I write it like that, I'm thinking, ooh, my little thought process here is, man, that looks an awful lot like a, 1 over the square root of x squared plus 1. Now there's an x out here. I'd have to think about that, but I'm thinking to myself, man, one of those square roots of x squared plus 1s or 1 minus x squareds, or whether they have a square root or not, they remind me of those inverse functions. And so just as a quick little recall, I actually have two little recalls over here, but from our formula list, the integral of 1 over the square root of x squared plus 1 dx is actually the integral of that root function there is equal to the inverse hyperbolic sine of x. So if we have that in our memory and in our reference sheet, we could say, oh, look at this. So I'm going to come in here and I'm going to say, let's start off with getting that natural log of x as a u. Start off with a substitution. So u equals the natural log of x. So then du equals 1 over x dx, which is perfect because take a look. This is 1 over the square root of the natural log of x squared plus 1. And I'm going to take this was x times that root. I'm going to write that as 1 over x dx. And look at that. I can make my substitutions now. So this is actually the integral of 1 over the square root of u squared plus 1 du. Oh, and man, we're getting close to something here. Now, I jumped over the bounds real quick, and we got to go back and fix our bounds or make sure we indicate that these were x bounds and carry our x bounds. I'm actually going to switch the bounds over to u because if x equals 1 and u is the natural log of x, then natural log of 1 is 0. So my lower bound is going to become u equals 0. And when x equals e squared, then my u is the natural log of e squared, which of course the natural log and the exponential cancel out, and my u becomes 2. So my upper bound is u equals 2. And now we can go ahead and use that integral formula. This is actually equal to the inverse hyperbolic sine of u evaluated from u equals 0 to u equals 2. So that's equal to the inverse hyperbolic sine of 2 minus the inverse hyperbolic sine of 0. Now, the reason I brought this second bullet down, right, our first little recall bullet here was for the integral formula, but the second recall was to remember that just like the hyperbolic functions have exponential forms, their inverse functions, the inverse hyperbolics, have logarithmic forms, and that goes back into some proofs and some derivations of those inverse functions, defining of those inverse functions in the introduction to the hyperbolics that's covered in Calc 1. But I just carried that formula here. This is how the inverse hyperbolic sine is defined. It is defined to be the natural log of x plus x squared plus 1. So if that's the case, well, we can actually simplify this. Of course, we could leave it in this form, but we could simplify this, and the inverse hyperbolic sine of 2 is the natural log of 2 plus the square root of 2 squared plus 1 minus the natural log of, when we plug in 0, we get 0 plus the square root of 1, which is just 1. So the natural log of 1 is 0, and this is the natural log of 2 plus the square root of 5. This is 0, so our answer is the natural log of 2 plus the square root of 5. And we can write our answer in that form. The inverse hyperbolic sine of 0 is also 0. So we would probably want to write it. So we could write it in its inverse hyperbolic sine form or in its logarithmic form. We're a little more comfortable working with logs, so it might help in our situation here to go to that. Also, if we wanted to plug this into a calculator, some calculators do have the hyperbolic and the inverse hyperbolic functions. Some scientific calculators do. Sometimes they're hidden in a menu. You have to look up further into the math menu to find those functions. But your scientific calculators definitely have logarithmic buttons on them. They're not even in it. They're definitely not in a hidden menu or anything like that. So if you remember, those inverse hyperbolic functions have their logarithmic expansions, their logarithmic forms. You can go to those to approximate on a calculator. Okay, we've done lots of examples through this overview of this chapter 7 with working with exponential functions, logarithmic functions, and the hyperbolic functions, both the hyperbolics and their inverses. And I think at this point we should feel pretty comfortable with all those formulas. It's a nice lead into our next section, which is just, again, review of the basics of integration. So did a lot of integral examples on this one and have some integral functions for you to practice on the worksheet and in the homework.